So the first speaker is the Dean Tai Nguyen, talking about the prediction of transient seepage flows in unsaturated porous media, so using SPH. So it's your turn. I'll let you speak.
Can you hear me well?
Yes, we can hear you.
Yeah. So hello everyone. Welcome to my presentation. So today I'm going to talk about the prediction of transient seepage flows in unsaturated porous media using HPH. So global climate change have triggered a lot of disasters such as flood or landslide. And then you can see for the figure, the video on the left hand side here is also really famous of the Tailing Dam collapse disaster that happened in Brazil in 2019. At the day it happened here, they killed like 270 people. Even they have the warning system with setting a near village. But the day we need the most, it not work. So for us, like academic or the geotechnical engineer, and then we have the question is that what can we do to minimize this problem? And in the case here, the understanding of the seepage flows or the interaction between soil, water, and air here is so really important. And the advanced computational geomechanics here is the key, not only to predict, but also to evaluate the consequences. And HBH here is highly suitable for this type of applications, but not only a solution. So in my talk, first, I will show you the computational framework and how to establish the seepage flow equation. After that, I will use the HBH method to solve this. And finally, I will validate some of the example. So first, you can see it here from the multi-phase mixture theory, we have the governing equation for mass conservation and the momentum conservation. And alpha here meaning that it's for alpha meaning that soil, water, and air. And if in the case in here, if you solve this each of equation, like you solve the equation for soil, for water and air, and this called the multi-layer approach. And in my talk here, we currently here we calculate the all of information for on one layer. And for the next thing here, so from the mass conservation, and we writing it out, and we will have the equation for soil, water, and air. And the thing you can see here that currently we are writing all of the resulting equation on the same solid phase reference framework. And then after that, we enforcing the linear relationship between the pore water pressure and the volume strain water. For the air phase, we apply the ideal Gauss law. And at the time, we have the new equation from the mass conservation that is for pore water pressure and pore air pressure. And in this equation here, the challenge thing is that we need to calculate this W here, which means the relative velocity. In here is between liquid and soil, and this is from the air and soil. And on the case that when you expand the momentum equation, and then you can substitute to the pore water and pore air pressure here. And finally, you will have the channel governing equation for unsaturated seepage flow here. So in this presentation, we are using a simplification here because in this here, we assume that soil phase is not deformable. And currently we are have not taken the influence of the gas phase. And for that, we have the final equation of the increment of water pressure head. And the thing here is that how to solve this equation. And then you can see here, there are two things we need to solve. First is this term, one on CSR, and the second term here is the second derivative. And all of the thing here from CSR here is that you need to solve this equation, is the relationship between the degree of saturation and pore water pressure. And then when you want to calculate that, in the case here, I will introduce you the soil water retaining curve here, high frequency model. This is the relationship between the suction and degree saturation. Actually, they have a lot of the high frequency model, like from Freeland in 1994 or Kosugi in 1996. And currently here in this presentation, I will show you, we will solve this equation by this high frequency model. And for the next here, going to detail, this is the relationship when we drawing it out. It's meaning that when the suction decrease and the degree of saturation here will increase to 100 here. It's meaning that saturated. And one thing you need to know is that a water conductivity model that link the hydraulic conductivity K here with the degree of saturation. And the three of the sample line here, I will use it for validate the case after that. So with this equation here, I have shown you that we can calculate this for first term, and this is the second term we need to solve for this equation. So the question we can right now is that how to approximate the first and second order derivative of a field variable. So in the case of this presentation, I will show you we're using HBH method to solving this equation. And what is the HBH method and how does it work? So HBH here is called smooth particle hydrodynamics, and it's the mass-free method in which particle carry field variable move with the material velocity. And you can see from the computational domain here, we had a cut slope here, and it can represent set by set of particles. And each particles here have the space. It's moved freely on the space. And when you want to calculate the information at a particular location, and you will use the interpolation process or weighting average. That means that you will taking the information of the neighboring particle to calculate the particle you want. And the key advantages of HBH you can see from here that we can simulate the massive large deformation like this. And then for the next slide, I will tell you so that about the function HBH approximation. And you see this key equation here, the F here, assuming that you have here is a field variable at a given location, like stress, velocity, or density. All you need to do is that you will taking the information of the neighboring particle, like particle J here, and then you weight it with the kernel function here. And then you multiply with the volume of the particle, summation all of them. And and more thing over is that the kernel function here should be symmetric and have a pell-shape. And you can go to the literature over there. This is beginning by Lucy and Gigo Monahan here, and Professor Bui is the first to apply HBH to the chill mechanics. And then you can also approximate the spatial derivative. It's so really very important to approximate the governing equation. So you can see from here, through HBH, if you want to calculate the spatial derivative, so even it's complex, the thing is that instead of calculate that, you will calculate the spatial derivative of the kernel function. This is an interesting feature of HBH. And with the two key equation here, it's forming the basic of the HBH. And if you want to learn HBH and you need to understand it, that's it. On the other hand, to solve the Transient Seepage flow equation, that I described in early section. And one we would need to do is that we would need to solve the second derivation by Seepage approximation here. So I will show you that the existing of the second derivative Seepage also approximation. So you see here, this is the equation from of the clearly Monahan here, and this is the equation from pressure Pui and pressure Nguyen here. And this is calculated for the Laplacian. It's meaning that the Laplacian here is that the second derivative for the x direction and the second derivative for y direction, summation of them. And you can see for the right hand side here, this term and this term is the same. Actually, the thing they added here is the error that you can see when you expand for the Taylor series. You can go to this paper and look at that. And for the next here is the equation from exponential driving guard. What is different in here is that this second derivative here, as approximation, that is we can calculate this term separately. It will really helpful when you want to calculate in an isotropic case. And again, you can see for the recent development of the second derivative here by Leon and Professor Bui here. And then the first term here actually really the same. And the second term here is the reduced error that you can see when we plot it with this order of the particles here. The errors is 8 plus with 8 multiplied with 10 power minus 3 instead of 3 here. So in my case, I will apply this Seepage approximation to approximate the increment of power pressure. And finally, we have this. So, and then for the next, I will show you, I will use it for validate some example. First, you will see this is one-dimensional case. This is the soil column, and this is the groundwater table with the height is 3 meters. On the top here is called permeable boundary. This is the initial condition. So you can see from here, at the beginning, all of the soil column here will have the same of the total height. And then we assign for the top particle, we will have the flux like this. And then you can see the total height here will change, it's increased. It's meaning that the water will infiltration from the top to the pot and make this soil column more saturated. And then for the second case here with the sun here, it means evaporate. And then normally you will see the total height here is 0. And then we assign for the flux is minus 0.002 here. And then the total height here decrease. It's meaning that the water will evaporate out. And then we compare with the analytical solution here. This is the relationship between negative power pressure head and elevation. You will see we capture well with the analytical solution. For the next here, you will see this is the validation with the 2 dimensions. So all of the example here for this about the Earth dam, you will see like this example. For the left hand side here, the groundwater level is 3.5 meter, and the right hand side here is 0.5. Yeah, is here like this. And then you will see our Seepage solution here will be able to capture the phreatic line. And we compare with couple of solutions with different method here. And it means that our proposed APS framework here can help well to capture seabed problems. And for all of these example from 1 dimension and 2 dimension, all you think is that you see that we are compare again the analytical solution or finite element method. And all of the simulation above is for isotropic soils, which means that we are using the same hydraulic of conductivity in all direction. But in reality, that soil is anisotropic. So that's what we do next is that we did further, we actually verify our model again, the experimental data. So you will see, this is the experimental data setup from the Kitamura 2007. he supplied the water at the top here, and the water flush is imposed on the upper surface here. And he puts the number of the sensors in here and inside the slope, which means that they can show us how pore water pressure change as the seabed flow progress through the slope. And in my case here, what I did is that I validate of the 10 sensors here. And then with the list of parameters here, allow us to basically to calibrate with our soil water characteristic curve. So this is the key idea of this case. And then you will see for the first, we will compare with the ABM. So for the isotropic case and an isotropic case, the excellent agreements between two numerical methods here are achieved all up across all the monitoring point, suggesting that newly developed HBS model could capture well the transient seepage flow problems. And you can see from here, for the isotropic case, the case X here, meaning that the permeability on the X direction here is lesser than isotropic case. And then you will see for the water here will infiltration here to the slope here faster than the case of anisotropy. And finally, we compare with the experiment, and you can see from here, we were able to capture quite nice against the experiment data. And you can see here, this result here represent the data as this location, 1, 2, 3, 4, 5. And this is 6 to 10 here. And the thing I want to say that we capture very well the seabed flow before the failure, but this location we cannot capture because we didn't consider the deformation of soil. So this is the next thing I'm going to do in my business journey. So thank you so much for listening.
Thank you for your presentation. Very different from, well, we are not doing a lot of continuous modeling here. So is anybody has any question?
Maybe I can ask a question if there is no question about the sorry, the law that is behind the constitutive law that are behind the SPH method. Can you give us more detail about them? I think you go through it, but it was a little too quick for me to grasp them. And for the infiltration, is it Darcy's law with some kind of Cosmic-Harman permeability or something different?
Sorry, can you
sorry.
repeat it?
For the infiltration of water,
yeah.
What is the constitutive law behind? Is it? I mean, I guess that the permeability of the soil is influencing the result in some sense. And what is the value that you take for the permeability? And is it something related to Cosmic-Harman or depending on the on the porosity or something else?
Do you mean the relationship between degree of saturation and water pressure?
Yeah. Okay.
Yes. So when you here, I'm going to this slide to show you. So what you say is that, so from we have the pore water pressure of any particle or any point. The thing is that the linking between the pore water pressure and the saturation here is that when you have the pore water pressure at that point and you can know the degree of saturation. So if you want to know that, you need a constitutive relation, and then you have to use the hybrid constitutive model. Yeah, is it?
Okay, this is how the pore water pressure reacts to the degree of saturation.
Yeah. So you see here, because we have when you solve and you have this equation, right? And with this equation, you have the increment water pressure head at a time. And every time the water pressure head changed, and this go to this question here, and we'll change this R here. This means that every time you have the different value of water pressure, and you have different value of the saturation.
Okay.
Thank you.
No, Ty, actually, Anton is asked about how the permeability change against, I mean, what factor affected the permeability change? It's a function related to the degree of saturation. Also, yeah, here, when you considering the deformation, the permeability will change against the porosity. Yeah, so that's the one that Anthony is asked about.
Yeah. Leon, do you have
And
any
also,
comment?
the K equation. Yeah. Okay.
Yeah, K. This function here, so K will be determined by the degree of saturation, and the K sub actually it would be the constant at the beginning, and when we considering the deformation, the K sub will change against the porosity, which is the Coase command theory. So we did considering this, but because in this presentation he just talked about the transition seepage flow in the rigid body, so the change of the porosity in the permeability I did not consider in this study here.
Yeah. Okay, thanks.
Yeah. Thanks, Leon. Any other question for Ty?
Yeah. 14. Yeah. Yeah, actually, this have no problem because the thing here is from the K set, the value of the K. This means that we just use the computer's time just more like than 1 hour. Yeah. 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 But so that's why recently here Lian has some of the time skip or semi here that we can have some achievement, because the thing is that when you have couple deformation and you have the time for mechanical and the time for hydraulic. So here I think Lian, can you have some comment on that?
You can try your best based on your understanding to answer the question. Okay. Yeah, so yeah, this is a really good question referring to the time scale. Normally for SPH, because it's the fully dynamic fully dynamic process for showing the moment equation. The time step for the solid phase is always very small in the scale of seconds. But for those problem like rainfall-induced rock failure, there may be several hours of the infiltration. So in our rainfall-induced rock failure paper, we have developed a different time scale approach, meaning that we, in the unsaturated infiltration process, we have a large time step size for the fluid phase, and still keeping a small time step size for the solid phase. And we assuming that during this infiltration process, there's no significant deformation that affected the change of the porosity, the change of the permeability, so that we can simulate it, those long-term infiltration using a large time step. But when the deformation occurs, then we can shipping back the time step from the fluid to the solid, so then they can have a same time step size for both phases, and then we can still guarantee the fully coupled mechanism between these two phases. Yeah. Yeah. Thanks.
Yeah, thank you.
Okay, I have a question now.
Yeah, please.
Yeah, I think we have listened a lot of prediction about the DM while you are using the Seepage. Can you talk about your understanding about the difference between DM and Seepage? Yeah.
Thank you for your question, Godong. So, for full of my standing is that FEM is the mass. We use the mass, and for the HBS method here, we are using the mass free, and that with our method is FES here we can simulate large deformation, which is so really tricky with the FEM, have the distortion of the grid. I think that's
sorry. I mean the DM discrete element method.
DM, yeah. Currently, I'm not go to this. Sorry, I have not.
So many tricky questions for a new PhD student.
He just started his PhD, so
he just started
really
PhD
difficult.
a few months, and you are asking so many tricky questions. Anyway, just a comment for other students as well. In my group here, we working a lot on the advancement of SPS for large-scale multi-physics application, and you probably will see that the application or the advancement of SPS for for couple of flow deformations, saturated, unsaturated, so have not been achieved in the past because of a number of issues, the stability, the accuracy, and so on. So recently we have achieved some good progress toward it, and Tai just started his new PhD, and what he did now is more or less repeat what Liang did, but he will move further on the unsaturated soil mechanics using predicting large-scale problem of landslide slope failure using SPS and advanced transit model. So you see a lot of things on SPS, and for the question related to Gudong, what is that difference between SPS and DEM? This is a totally different approach. SPS is the continuum-based approach, which is similar to FEM, except that we're using a particle to solve the governing equation. And the particle in SPS, it represents the continuum field, which is totally different from DEM, where the particle more or less represent the grains. Okay, so this is a totally different approach. So when you think of SPS, think about FEM, finite element methods. Okay.
Thank you, Professor.
Yeah, I think that's come to the end of Thai presentation. We're a little bit behind the schedule, so I think we now can move to the next presenter. Yeah, so Lian, you